Welcome back, everybody. Welcome back. Glad to see you've decided to tune in again to Nick Does Maths with me, Nick, and this maths. What do we have today? We have a second order differential equation. It's all over the place. It's all over the place. We got x cubes loitering. We don't know what to do, but we are going to attempt the substitution x equals z over a half. We're going to reduce this into something much nicer. We are changing the variable. Right, so what we really want to do is we want to be able to go from dy dx to something in terms of dy dz, or dz if you come from across the pond. That just involves a little bit of chain rule. Now, what's our chain rule that we're going to use? Thank you, red pen. Thank you, board eraser. We're going to use the fact that if I want to differentiate something with respect to x, that is the same as differentiating with respect to z, but we also need to multiply by dz dx. That is our basic chain rule. Okay, that is our chain rule. So if I want to differentiate y with respect to x, I will pick up a dz dx, which means I probably want to write this in the form z equals x squared. So dz dx is 2x times dy dz. Now we can tidy that up a little bit because x, of course, is z to the half. So that is 2z to the 1/2 dy dz. This question is exactly why my z's have a little bar through the middle, because otherwise there is no way on earth anyone is telling my 2's and my z's apart. Right. The second derivative. Well, we have to realize, of course, that that is just the derivative of dy dx, which means that I'm going to differentiate dy dx. Now, I just said that dy dx is 2z to the half dy dz. Now, how do I differentiate that with respect to x? Well, we set it up here. I pick up a dz dx, which was my 2x, times, I need to differentiate this with respect to z. And that will just give me a product rule. Now the x as well, up there, that's 2z to the 1/2. Now let's differentiate that with respect to z. Differentiate 2z to the half, that is 1 over z to the 1/2, keep the dy dz, plus keep the z to the 1/2, differentiate the dy dz. And if I multiply that all out, I will get 2 dy dz plus 4 d2y dz squared. Okay, right. That's a lot of stuff. That is a lot of stuff. Let's start substituting stuff in. Where do we go from here? We get x. Now I'm going to substitute everything in as much as I can. Sure, why not? X, which is z to the half. Times d2y dx squared. Now, we just established that that is 2 dy dz plus 4 d2y dz squared minus dy dx, which is 2 z to the 1/2 dy dz. I need more space. I need more space. I know what I'm going to do. I know what I'm going to do. So let's just recap some of my transitions here. We have said that. So we've established that dy dx is 2 z to the half dy dz. And we've also established that d2y dz squared was 2 dy dz. Right. Less cramped, more space. Let's get our new differential equation down here. So what were we saying? We were saying that x was z to the half times 2 dy dz plus, that is not what we got. Quick check. It's 4z. d2y dz squared, that's what it was. There we go. Minus 2z to the 1/2 dy dx minus z to the 3/2 times y plus z to the 5/2. Now this happens quite frequently, which is kind of cool. What we'll notice is these two terms here, they go bye-bye. So what am I left with? I am left with 4z to the 3/2 d2y dz squared minus z to the 3/2y is equal to minus z to the 5/2. Now I can divide everything by z to the 3/2, so that gives me 4 d2y dz squared minus y is equal to minus z. Isn't that nice? So let's pop that back up here. 4 d2y dz squared minus y is minus z. Okay. Now this we can solve. We can solve well good. So complementary solution. 4 lambda squared minus 1 is 0. That tells me lambda is plus or minus 1/2. So that's nice. So we've already got our complementary solution a e to the half z plus b e to the minus 1/2 z. Now we need to find the particular integral, the private investigator. Nice and linear. Let's try a nice linear function, which does mean, of course, that d2y dz squared is 0, so awesome. Let's plug that in. We probably could have just done this by inspection. That tells me that b is 0, a is 1, which gives me y is ae to the z/2 plus be to the minus z/2 plus z. And then finally, let's put that back in. Z is, of course, x squared. So the solution to this is y equals ae to the x squared over 2 plus be to the minus x squared over 2 plus x squared. Smiley face. It's quite nice. Almost a horrific accident there with me leaving that z out for the d2y dx squared. But we got there. We fixed it. I saw it. I was like, that doesn't look right. It doesn't feel right. Voila. Plus x squared. Yes, plus z, so plus x squared. Yes. Yes, yes, yes. And if you really have time at home, you can always plug that back in to my original one and make sure that it works. Whatever floats your boat of an afternoon, right? I won't lie, it's a little bit tempting, but I have kept you for long enough. So, before you go and carry on with your day, please, please remember to subscribe, like, hit the bell, all that cool stuff, so you know when the next little bit of mathematical loveliness is coming your way. In the meantime, stay tuned for more. I'm Nick, this was Maths. See you soon.